So in the last recording, we left off talking about the different parts of movement of water. And the next step is how water moves relative to scale and Reynolds numbers. So to review from last time, if you look at a flowing system from the side, and we have flow going from the left and the right, and these are the flow vectors in this system, you can see that in the open channel, flow is turbulent, right? That the vectors are not all completely straight. But as you get smaller scale and closer to the solid surface and the water velocity decreases, it becomes laminar. That is, the streamlines are parallel to each other and you don't get much up and down mixing. When you get right at the edge of the surface, it slows more and more. And then when you're right against the surface, the water is not moving. And so Brownian motion is going to be the only movement. Those water molecules will be jiggling around, but they will not have net movement downstream. If you had a more viscous liquid, this would happen more closely. There's some curious things that happen related to this and Reynolds number. What you can think of is the hydrogen bonds of water are holding on to the other molecules, and they're also holding on to the wall. So when you get out in the open channel, the wall has no influence whatsoever on the movement of the water. But as you get closer, it's basically the friction of being next to the solid surface is transmitted by those hydrogen bonds through the fluid. And so that's why you're getting a slower and slower movement and eventually no movement at all. The curious thing about this is that if you are a microbe and you are swimming down in here, the wall actually influences or impedes your movement. It's basically is holding you back. So if we look at a microbe on a slide, right, and measure how fast it's able to swim, that will give us a skewed version of how fast it's able to swim in the open water. It might be relevant to how fast, let's say, a benthic organism, an organism living in the sediment on the bottom, could swim, a microscopic one, because then they're always close to the surface. This is extremely different from the way we experience water. If you are swimming next to a wall, like the corner lane on a swimming pool, you're not going to be slowed down by that wall any appreciable amount. And so this gives rise to the idea of the flow boundary layer. And essentially it's an idea of where the flow is laminar and where you're at 99% of the open channel velocity. And we see this logarithmic decrease in flow, water velocity, as we get closer and closer to the surface. So this is another place where scale matters. If you are a large fish, a big catfish, right, you're living in a turbulent world. And being in the flow boundary does not have much effect of you at all. If you're a microbe, you're always essentially in a very viscous world, and you're not experiencing much turbulence at all. If we look at the flow boundary layer, it can be variably different. And this is a little bit of an artificial construct, because if you really have turbulent flow, you can get these turbulent excursions down in, you get this random stuff, and all of a sudden there might be enough force to push flow down in there. So it's just sort of a fuzzy area that's convenient for us to think about how flow works. In this diagram, we've got a flow from the left to the right, and the outer edge of the flow boundary is seen here. As you can see, if this rock that's in the stream has a high point right here, the flow boundary is going to be considerably smaller. If there's a valley in here, there's going to be considerably deeper, further to where the flow is open, turbulent in the open water. And then the other aspect of this is that the effect of this substrate is propagated downstream. So you get a thicker and thicker flow boundary layer the further you go downstream. Remember, if we go back to the Reynolds number, that the characteristic length was important. And so this is what I was talking about there. Let's just pop back real quick if I can get it to do that. So if we look at the Reynolds number, the characteristic length is here. And the longer things are, the less viscosity it experiences, right? So we go, this length here is influencing the action that things have on there. So the longer things are, the less viscosity there is. What you're doing then is basically pulling that back. So now we can think about streamlining in Reynolds numbers related to this. If we look at flow that is at really low Reynolds number, or this could be an object swimming through, or it could be an object sinking, or it could be an object trying to stay stationary, being stationary and having flow going around it. It's all relative, right? So at very low Reynolds numbers, that would be under A and D, flow is essentially laminar, and it's going to slip around there. As we crank up the flow and get our Reynolds numbers between 5 and 100,000, we start getting turbulent vortexes. And then you get fully turbulent flow when we get above about 100,000 Reynolds number. This means that there's this pullback on this object. So this object here, these objects here, will have more drag than the objects that are experiencing less turbulence. When we get to these turbulent flow here, you can start getting turbulent flow, but not fully turbulent flow. And that's why race cars are streamlined, airplanes are streamlined, birds are streamlined, large fish are streamlined. All those things are moving through fluid fairly rapidly, and they want to minimize the amount of turbulence that they're shedding behind them because that wastes energy. The transition between where this kind of thing happens is sort of roughly around about 1 millimeter or less in size. So if you think about a larval fish versus an adult fish, what's the difference in form? Those of you that are into fishes. I'll take either a talk or a chat.
Can you repeat the question?
What's the difference in body shape between a larval fish and an adult fish? Well, particularly one that's going to be big, you know?
There's a difference in surface area.
That's partially it. You know, right when they hatch, what's going on? What do they oftentimes have attached to them still? Right.
A yolk sac?
Yeah, they'll have a little bit of a yolk sac on them. And then, yeah, and Lane got it. Larval fish are chubbier, right? They're kind of blunt, you know, and they're not very streamlined, but they're really small, so they don't necessarily need to be. As you get large, you know, as you turn into a trout or a walleye or something that's big and swims fast, right? You're going to get more and more streamlined. And as we look at things like zooplankton, something like Daphnia, it's not streamlined at all, but it's a sub-millimeter sized particle, so it doesn't really need to be. And the aquatic invertebrates are sort of somewhere in between that. And of course, this is predicated upon something needing to be in water that's moving quickly. So you can have some fishes that are pretty blunt, but they live in very still water. So, and they tend to not be so streamlined. And certainly some macroinvertebrates that are that way. So this is one of the evolutionary forces, and it's related to moving water, number one, and Reynolds numbers, so spatial scale. This is just an actual physical image. It happens to be of a marine alga of turbulence as you increase flow. And they just put mica particles in the flow, and the mica particles line up with the flow lines. So you can see how laminar the flow is up here. So you just get these streaks of laminar flow coming in this particular system. And then as you go downstream, it's somewhat laminar. There's not much mixing, but as you go increase in your water velocity, you go up to fully turbulent flow. Even though it's coming in laminar here, you get fully turbulent flow. So even things like aquatic plants are going to need to streamline and high flow, or else they'll wash away. And I have a question here, why would an attached plant need to evolve a way to streamline? But I think I just answered that, so I guess I'm not going to ask that question for real after all. So we have sinking rates of small spheres is also a function of size and density of the sphere and viscosity and density of the water. So some cells can alter their shape to change sinking rate. So this is a measured sinking rate of the diatom Melisira italica. It's a filamentous diatom, and here's a picture of it. And this thing is probably 30 microns across and several hundred microns long, like a tenth of a millimeter long, right? So what it's doing is getting long and thin, and it can be planktonic. And we see that as it increases in size, what it's doing is it's adding cells onto this chain, right? And if we have on the x-axis the volume in thousands of cubic microns, and the sinking velocity, micrometers per second, and we have a sphere of the same density as that's in the range of densities of Melisira, we can see what the sinking rates are be as those spheres increase in size. So this 1.09 grams per centimeter cube is about the lower range of density of the Melisira. And we see that as it gets larger and larger, it's going to be sinking faster and faster, whereas the Melisira is barely sinking faster as it gets bigger. And if we have a sphere near the maximum density of Melisira, it sinks really fast. It always is sinking faster than that Melisira. So this is an evolutionary effect. It also has effects on inorganic particles as well that are important. So what was a defining characteristic of the difference between the two ponds that we were at, the Willow Lake and the Tuttle Puddle that was on the other side? What was the real difference between those two on Tuesday?
The movement of the water. It seemed like the one we were at, you guys said it was more stagnant and water wasn't always flowing in to it.
Right, and it was green and there's a lot of algae floating around in it. And what did the one on the other side look like?
It was a bit more brown, almost more like silty.
Yeah, it was turbid. Basically, there's a lot of clay coming in from outside. That clay takes a long time to settle out. So what we'll see is that if you got a fine clay and you shake up a beaker of water with fine clay and set it in the lab, right? You come back in a day and there's still clay. That's because those particles are really small. The Reynolds number is low or high with the small particles. Okay, so I'll just do a question of the day now since nobody's answering. Everyone has to answer in the chat. Does a smaller particle sinking experience a smaller Reynolds number or a larger Reynolds number than a larger particle? Small particle sinking, does it have a smaller or a larger Reynolds number than a larger particle? Everyone got a chance to answer? What if I say it was larger? Can somebody convince me it's not larger? Why is it smaller? Billy, why? Are you there, Billy? You're unmuted, but you're not talking. I can try somebody else if you don't want to answer. How about Gabriel? Do you have an answer? I'm not getting much answers here.
Is it because it has a smaller surface area?
Yeah, smaller surface areas, the smaller particle. Remember, Reynolds numbers are a function of surface areas, right? And that's a really small surface area, so it's going to have a low Reynolds number. It's going to be experiencing more viscous solution. It's going to just take longer to sink, and any small current will push that water up and not allow it to sink. Good. Yeah, I knew everybody typed what everyone else did, Emma. That's why I asked. That's why I wanted to tell you that you all had the wrong answer to see how many changed your answer. I wanted somebody to be certain of it. All right. Okay, so if you want to design an object that sank the most quickly, what do you do with respect to size, shape, density, and why? So we already talked about size. Do you want it to be big or small?
Big.
Big, right? Want it to be big. Good. So if it's big, what shape do you want it to be?
Spherical.
Maybe. There's a better shape. Hey, Emma got it. Streamlined. Yeah, you want a streamlined object, right? So once you get it big and you get it dense, somebody said high density. A couple people said high density, right? It's going to be sinking fast. So if it's sinking fast, then it's going to be turbulent flow. So you want to have it be streamlined as well. So things that I talked a little bit about, those conductivity depth temperature probes they use in the ocean. They send them down wires. They're just shaped like little rocket things, and they go down in the ocean and measure the chemical, physical parameters very, very quickly. Good. So it's all ties back to Reynolds numbers, and I'm not going to let you forget about Reynolds numbers. I'm going to come back to them. So remember this, figure it out. If you've got any questions, you got to ask me. So the next step after, now that we're out of Reynolds numbers, we've talked about is hydrologic cycle. The solar energy and gravity, wind, the Coriolis effect, and organisms are the things that move water. So we think about spatial scale and water movement. We've already started talking about this. At the size of a bacterium, or less than about a millimeter, right? We can have Brownian motion, molecular movement of water. So they're moving really rapidly, but they're not going much of any particular direction.
Is molecular movement, you're saying that's synonymous with the Brownian effect?
Yes, the Brownian effect is a result of the molecules bouncing around off each other, and a small particle gets hit by an uneven number of other moving particles at the same time.
Okay.
So it's moving, it's kind of jiggling around, but everybody's jiggling around at that scale.
Gotcha.
And then the next, we get up into laminar flow region, then the turbulent flow region, and then we have these really large currents in the ocean and hydrologic cycle. And the hydrologic cycles we'll get. Oh, Emma said, yeah, like those rubber torpedoes you play in the swimming pool with. Yes, going back to our previous thing, that's a perfect analogy. That's why those things are shaped like torpedoes, and they can really glide. So we're going to talk about movement of light, heat, and chemicals in water. We're going to talk about now diffusion in water and light and heating of water. So first we got the movement of the water here, and then we're going to talk about movement of light and materials through the water.